So howdy ho, and thanks for joining me to listen my lecture regarding the spherical and cylindrical waves. And of course, what we will be doing here is that I will be shortly stating that depending on the problem at hand, we should choose the coordinate system accordingly. And sometimes spherical coordinate system is the smart choice. So then I will be showing to you that how we can transform from spherical coordinates into the Cartesian coordinate system. The other way around, of course, can be found from the internet, and maybe there will be a homework exercise regarding that. Then I will be showing you how we can describe a spherical wave, and this is of course nice in our context of this course, so that in case when we need to describe spherical waves, we can easily do that afterwards. And then I will be afterwards focusing on the cylindrical coordinate system, and I will be showing you how we can transform from the cylindrical coordinates into the Cartesian coordinates, and of course the vice versa would apply equally well, and then how we can describe a cylindrical wave. And then finally I will be concluding that in most of the time when we are in the so-called far field approximation, so when we are looking at the wave that is very far away from the actual wave source, we can approximate things as plane waves. And that's our rudimentary motivation of then resorting back to using plane waves mostly in our description in what follows in this course. But of course, all kinds of waves, as I've all said it before, all kinds of waves can be described using all kinds of coordinate systems. So maybe sometimes it's not the easiest way of describing things using plane waves if you have spherical symmetry, but it can always be done. That's my point. So if you're good with math and smart, you can always use whatever mathematical tools when you do things right. But sometimes when you're smart and lazy, then choosing the right tools will really help you out in terms of the mathematics. Let's now get started. So like I promised, I will be saying first a little bit about the general motivation. So depending on the symmetry of the problem, the issue at hand, it may be smarter to change your coordinate system. So for example, a prime example would be that if you would want to integrate the volume of a sphere, this is a very difficult task to do in a Cartesian coordinate system, but it's very trivial to do when we are changing into the spherical coordinate system. And similarly, it would be quite devious to do in a cylindrical coordinate system. So these are the kind of like examples that you should think of when you are looking at a problem at hand. Sometimes your problem is symmetric with respect to a single point in space, and then it's really often smart to move this point to be the origo and use spherical coordinates. So if things look identical in all directions when you are going away from this single point, then spherical coordinate system might be the smartest of choices. But of course, this depends a little bit of intuition and understanding, when to transform and when to not. See, this point, when we want to describe, like in a Cartesian basis, we would be using coordinates x, y, and z. And now what we must do is that in the spherical coordinates, we should be using r, that's the length of my vector r, and we have the two angles theta and phi. So theta is the polar angle and phi is the azimuthal angle. And r is the distance from the origo to this point r. Here is the coordinate system how we define these different angles. So now we have the origo here, and in the x, y, and z would give me the Cartesian basis. And then in this point, x, y, z, and denoted with r, if I would want to describe this point in the spherical coordinates, I would be using the length of vector r, and then I would be using the polar angle theta defined as the angle with respect to the z-axis and vector r, and then I have my azimuthal angle defined with respect to the angle from x-axis to the projection of the vector r into the xy plane. And the kind of connection between the between the coordinates is that the x can be written to be r times sine theta times cosine of phi. The y can be written that is the r times sine theta times sine phi. And z can be written simply as r times cosine of theta. And here, of course, theta is the polar angle, phi is the azimuthal angle, and r is the distance from the origin of my coordinate system. So here's the connection. So if you have already a way to describe your point using the spherical coordinate system, this is how you can easily calculate your XYZ coordinates. And of course, the vice versa, you can find similar kind of equations from the internet. Or from our booklet, I think. We don't derive the equation for the spherical wave, but of course, what we would do is that we would transform the Laplace operator into the spherical basis, and then we would solve that differential equation in that basis. And the end result would be a spherical wave. But we do not do that here because the Laplace operator is somewhat non-trivial in the spherical coordinates, so it's just devious. It's not overly complicated, but there's quite a bit of math involved. But the end result, of course, is quite clear. So the spherical wave can be easily written, and the spherical wave would be of a form that now it depends on r, the position, and on time. And then I have my amplitude, a0, divided by r, the length, and then I have my exponent I plus minus kr minus omega t. So here, this is really the case. I have my k, the modulus of my wave vector multiplying the modulus of the position r. And the interesting thing here is that for a spherical wave, the amplitude, we want to have this 1 over r dependence here, so that the energy is being conserved when we are going into further away from the origo. So this is the kind of difference that we have in a spherical wave than compared to, for example, a plane wave. So that in order for the energy to be conserving, when we are moving away from the origin of the wave, the energy must be remaining the same, so that then the amplitude must be getting smaller. And the signs plus or minus there before the kr term is that the plus sign corresponds to an outgoing or diverging wave, so that a wave that is leaving out from the origo, and then the minus sign means that then we would be having a wave that is incoming or converging into the origo. So basically they tell the direction of propagation of the wave with respect to the origin point. So this is the kind of notation that we have. And of course, depending on the situation, you may need to use either. Either you need to have an outgoing wave or you need to have an incoming wave. Depends really on what happens. If you have a source and you want to describe how that source emits radiation, then you really definitely need to be worrying and working with the plus sign. So definitely the emitter acts as an outgoing source of radiation. But if you, for example, are focusing light into a small point, then you would want to describe things using incoming rays. So you're focusing light into a single point, so that's where the energy is propagating, heading into the origin of point. Here, if we look at the mathematical way, how the spherical wave looks like, definitely it's spherically symmetric because we only have the dependence on the distance from origo r. So we don't have the theta, phi dependencies in that equation at all. And what this tells to us is that when we are thinking of the phase fronts of spherical waves, they are also origo-centered spheres, as makes sense. And the amplitude, of course, decreases, as mentioned already, is that the maximum of the psi will be scaling as 1 over r. And this is the amplitude. And when we are thinking of the kind of intensity or irradiance of the field, then of course it scales as 1 over r squared. So that's where we get the usual 1 over r squared law, power dependence. Sometimes we now know everything about spherical coordinate system and spherical waves. Sometimes we instead want to represent the problem using cylindrical coordinates. And here's the coordinate system and the transformation. So again, we have still x, y, and z directions. Now we have the same point, r, but now we are describing it not using spherical coordinates, but the cylindrical coordinates. So we have the theta, and this is the angle defined with respect to the xy plane. and the projection of vector r into the xy plane, and then the angle with respect to the x-axis towards this projection. Then we have the length of the projection, that's denoted with rho, and then the z coordinate will not be changed. So we just project the vector r along the z-axis, and then we get the z coordinate system. Sorry, z coordinate. So the point r in the Cartesian coordinates is related to the cylindrical coordinates via quite simple relations. So x equals rho, that's the length of the projection along the xy plane, multiplied with the cosine of theta. Theta is the azimuthal angle. So in spherical coordinates we have the phi representing the azimuthal angle. Many times in cylindrical coordinates we are instead using theta as the angle, but the physical meaning is the same. Then we have y coordinate, and this is related to the rho and sine of theta. And then we have the z coordinate, and this is the interesting point here. The z coordinate remains unchanged when we move from the Cartesian coordinate system into a cylindrical coordinate system. And now it kind of makes sense also why we call it cylindrical, so that the things don't really change in the transformation with respect to the z-axis. And this is the kind of axis of symmetry in these spaces. So rho is the distance of point r from z-axis, so the projection in the xy plane, and theta is the azimuthal plane. If you would want to find a solution into the wave equation in cylindrical coordinates, this would be even more cumbersome and tricky than in the spherical case, but the actual result is quite simple, especially when we are far away from the z-axis, so that the cylindrical wave far away from the z-axis looks roughly like a amplitude a0 divided by the square root of the rho, and then we have the phase function exponent I plus minus k times rho minus omega t. So this is very similar to the case of a spherical wave, but the power dependence is slightly weaker, and this is what we should remember. What's the difference between the spherical and cylindrical wave? But the phase function looks exactly the same. So this is the phase evolution that we have. So we have the rho coordinate there giving us how the phase evolves. And the main thing here to remember in what follows in our course is that, of course, when we go far away from the point of origin, both the spherical and cylindrical waves, they really resemble plane waves quite much when we are far away from the source. So graphically put, I hope you remember this picture, is that when we have our source of light and when we are very far away, the phase from there, denoted with the blue, is basically planar when we are far away from the source. So this is the kind of main message here. Depending on the problem at hand, you might be benefiting of using spherical coordinate system or cylindrical coordinate system, or spherical waves or cylindrical waves. But most of the time in optics, we are dealing with a far field situation, and then the kind of nice mathematical object that can be used to describe things. Most of the time it's just plane waves, so that the phase front here is almost planar anyway. But sometimes we want to, our problem is close to the source of light. For example, we are looking at the emission of molecules very close to the molecules. Then we would be tempted of using spherical waves to describe things. Or vice versa, we would be focusing down a laser beam into a very small spot, and then we would be very tempted of using spherical waves. But it depends entirely on the situation. And like I said, it's really a matter of taste, that everything can be described using all sorts of waves, but sometimes it's just way easier to use a smartest way of describing things. So just develop some kind of laziness in your treatment, that what kind of math you want to apply in your problem at hand. So this is what I wanted to say today. I hope you enjoyed this lecture, and please join me quickly when we are having the last 2 lectures on this chapter, where we are really now going into the vector calculus of things. And this is, of course, providing us the motivation so that in the next week we can encounter the Maxwell's equations in all their glory and be happy about it. So thanks for your time and patience. Bye-bye.